In the last video, I gave you a very simple demonstration of using a parallel stream using an intermediate operation. But even with that simple example, we learned that it's not always a straightforward decision whether to use parallel operations or not. Nothing is free in life generally, and that's true of software too. So even though it's easy and seems like it would be a good idea to always use parallel streams when you can, there are some very good reasons not to do so. In this video, I'll continue to show you some of these considerations. Obviously, in the last example, when we got the average of a million numbers, the order of the elements being processed didn't matter. There are cases though where you might want to process an ordered stream. Doing this with a parallel stream is possible, but again, depending on the size of the data, it might not get you the performance gain you were hoping for, since ordering requires a synchronization process and time to sort. Let's consider a couple of ordered operations in the next sample of code. I've created a new project called Parallel Streams and More with a new main class and method. Before I do anything with streams, I'll create a record for a person. I'll include this in the main.java source file. I'll just have each person have a first name, last name and age. I'll randomly assign each person's name and their age. For the first and last names, I'll create a short array of 6 values to pick from. I'll start with a private final static array of strings with 6 possible first names specified. I'll use names that start with the letters A through F, so Abel, Bob, Charlie, Donna, Eve and Fred will do. I'll do the same thing for last names, but use N through S names, so Norton, O'Hara, Peterson, Quincy, Richardson and Smith here. I want a random number generator, so I'll set that up as private final and static as well and initialize it. I'll create a custom constructor. I'll just code this manually. I'll make the constructor public and no arguments since all the fields will be generated. I'll get the first name randomly from the first names array and I'll do the same for the last name. And the age will be a random integer between 18 and 99, so my upper bound has to be 100. Finally, I want to override the toString method. I'll insert a generator toString, but next select none for the fields. I'll remove the generated return statement and instead return a formatted string. I'll print the last name first, a comma, the first name, and then the age in parentheses. Okay, so with this record, I can now use it to run some tests with parallel streams. Getting back to the main method now, I'll generate a list of 10 persons. I can use stream.generate, passing it the method reference for a new person. That gives me an infinite stream, so I'll limit it to 10. I'll sort by the last name using the sorted intermediate operation and passing in a comparator derived using the person's last name. Again, I can pass that as a method reference. Finally, I'll print each record using the for each terminal operation. Running this code, I'll get 10 persons with randomly selected last and first names. Because I have such short lists to choose from, I may get duplicates, but the names will be printed in order by the last name. Now, let's now make this stream parallel. I can add that right after the limit operation. If you're observant, you might notice that IntelliJ has grayed out the sorted operation. I'll come back to that in a second, but first I'll run this. So regardless of whether this operation was faster or not, in parallel, you can see we've got a problem. My persons aren't sorted right. Let's highlight the sorted operation and see what IntelliJ has to say about it. Redundant sorted call. The subsequent for each operation doesn't depend on the sort order for parallel streams. Replace the terminal operation with for each ordered. What does this mean? Let's hover over the for each operation in IntelliJ. This pops up the API documentation. What I want you to read and understand is that for parallel stream pipelines, this operation, meaning the for each operation, does not guarantee to respect the encounter order of the stream. Doing so sacrifices the benefit of parallelism. If you want things ordered by parallel processes, you have to do things a little differently at the expense of some of the benefits you might get from parallelism. I'll comment out the sorted operation, and I'll change for each to for each ordered. Running this code, I can see this isn't sorted in any way that I can see, so what does for each ordered really mean or do? This is a bit easier to see if we save off some persons in a sorted array, then use the sorted array in a stream. I'll insert the code to do this before the stream.generate method. This will look like the code I already have, generating 10 new persons. Again, I'll limit the stream to 10 for now. I'll include the sorted operation again, sorting by last name only. And I'll call the toArray terminal operation. I'll next add the code to print this generated array out. I'll loop through the persons array. Then print each person. I'll include a separation line. Before I run this, I'll change my second stream to use this array as the source. I'll run this now. You can see the array is sorted by last name. And now the stream that is sourced by this array is also printed in the same order. I'll change for each ordered back to for each and run that again. Now you can see that the second set of names is not ordered, not in the stream sources order here. So the for each ordered operation guarantees the order to be the same as the stream sources order. It doesn't guarantee that the stream will be sorted. Using the for each ordered method on a parallel stream is going to increase the overhead of the parallel processing. To figure out how much overhead is incurred, you'd need to do metrics on your pipeline using different data set sizes as I did in the last video. I won't cover that here because I want to cover two other topics, reduction and collection, using parallel streams. First, let's look at a simple reduction on a parallel stream. I'll add another separator line. I'll get a stream of integers from the int stream class using the range method. The second argument is an exclusive upper bound, so if I want a list from 1 to 100, I need to put 101 as the upper bound. I'll make this a parallel stream. I use the reduce terminal operation that takes two arguments, the identity which both creates and initializes the value, and the accumulator which adds value. Here, it will just be the sum. I'll print the sum. Running this code, I get the correct sum of the numbers, 50-50, using parallel processing with a reduction. Again, you'd want to benchmark your timings, but you'd expect that at some point getting the sum of a large set of numbers using a reduction method like this would tip the scales to being better performant in parallel. Let's look at another reduction though, using strings. I'll set up a text block with a familiar nursery rhyme. I'll call it Humpty Dumpty and quickly type up the rhyme here. I'll print a separator line. I'll use scanner with the text block as input and get the token stream to get a list of words. I'll print the words out and I'll print another separator line. I'll run this. I'll see each word, or token from the scanner in this case, printed on each line. So now I'll use a stream to put Humpty Dumpty back together again. I can do this with the reduce method using the method that takes three arguments. These are an identity, an accumulator and a combiner. I'll use a new string joiner with a space for a delimiter as the identity. The accumulator will be the add method on string joiner. Finally, the combiner will be the merge method on the string joiner class. I'll print the result out next. I'll run this code, and you can see that worked using a serial stream. The nursery rhyme was reconstructed from my list of words using string joiner with a space. I can change this to a parallel stream by changing stream to parallel stream. This is the second way to get a stream. Like the stream method on most collection classes, most also have a parallel stream method, which I'll use here. Running this code may have unexpected results. I usually get one of several different exceptions, but occasionally I'll get an empty string result. So what's going on here? Well, it turns out that string joiner isn't thread safe, and these errors are being caused by interleaving threads. I'm going to replace this code, this reduce method, with a special type of collector operation instead. I'll first remove the entire reduce operation. I'll then add a collect operation, and as the only argument, I'll call collectors.joining, passing that a space in quotes. This method uses a string joiner, but in a thread-safe way. I'll run this code. This code completes and prints out the nursery rhyme correctly. I'll run it a couple of times. And you can see this works each time. Instead of string joiner, I'll try a different reduction operation. This time, I'll use strings and string concatenation. This time, I'll use the two-argument reduce operation, so the first is the identity. I'll pass a new empty string. The second argument is an accumulator. In this case, I'll pass a lambda that concatenates one string to another, then concatenates a space after that. I'll run this code like this. Notice that this code seems to have different numbers of spaces almost randomly throughout. When you run a reduction in parallel, each thread will use the identity to create a new instance. It will then start processing some part of the data using the accumulator to combine its queue of data. It will then again use the accumulator to join its reduction to other threads' results. I'll revert this last update so that I revert back to a parallel stream that works correctly. Parallel streams are great in some cases, as you can see, but can get complicated in others. You can't just flip a stream to a parallel stream without some due diligence and thorough testing. I want to show you one more example with a collection, this time getting a map back. I'll set up a variable named last name counts that will be a map with a key that's a string and value that's a long. This will be the count of persons that have the same last name. I'll generate a new set of 10,000 persons. I'll process these persons in parallel. I'll use the collect method, passing it collectors.grouping by, I'll group by last name, and get the counts with the counting collector. Lastly, I'll print this map each key value pair. I'll run this, and I'll get each last name printed with the counts of each that were on this stream. You can see there's a pretty good average distribution of counts across the 6 last names of our 10,000 randomly generated persons. I'll add a little bit of code to add these counts up. I'll set up a total variable, initializing it to 0. I'll loop through the values in the mapped results. I'll add each value to the total. Finally, I'll print that total out. Running this code confirms that the counts equal 10,000. Although you can use grouping by with parallel streams, Java states in its API for this method that the merge method of combining multiple threads maps is very costly, and that using grouping by concurrent is much more efficient. The collectors.grouping by concurrent method will return a concurrent implementation of a map. In the next video, I'll be discussing what this means and what concurrent collections are, so I'll see you in that video.